Okay, so I think let's get going with this. It's 35 slides, and I think much of it is very easy to digest, so I think we will go through it very quickly. Even the diagnostic testing, maybe we just come back to the details of one or two tests specifically as needed, specifically the stability tests. The other residual diagnostics are kind of very straightforward. So basically we have two jobs now. Once we are at that point that we now have the long run, steady state co-integrated relationship, how do we use that information to build the error correction model? Which then brings more, it also brings the dynamic adjustment in periods of disequilibrium. And then once we're at that point, since the ECM, the error correction model, only contains stationary elements, we have to perform the standard diagnostic testing. The residuals must be well behaved, normal, no zero correlation, no heteroskedasticity. The relationship must be stable, and we will define that. And then also just think a little bit about the consequences and how we fix problems if we encounter them. So maybe a little bit of a wrong perception sometimes. We see that ECMs are referred to as short-run models. And the thing is that the error correction model, yes, it does contain short-run components, but I still think the essence of what's in the error correction model is the long-run relationship. So the ECM is not a short-run model. Where it becomes a short-run model is that many of you already mentioned. What if I don't find co-integration, I difference the data, and I run a model in first difference data, no long-run component. That is when an error correction model can be a short-run model, but then it's no longer, then there's no longer any error correction in there. So an ECM cannot be purely a short-run model. Then it's a short-run model and not an ECM. So we estimate that long-run steady-state relationship, and we know that that is rarely observed. That's why we're also interested to model that short-run dynamic adjustment. Reasons why systems are not in equilibrium? Why would that be? In real life, all kinds of exogenous events happens, and it's not so quick and easy to adjust to new information. If suddenly demand lowers for the fact that the financial crisis lowered international demand for our goods, it's not so easy to immediately just produce less. You cannot just lay off people, and sometimes raw materials have been ordered and all of that. So that adjustment is not instantaneous. Institutional and structural change, that's something that we have to deal with and adjust to. And then even the concept like bounded rationality, that is where we take decisions at the time based on the knowledge that we have, but it's not an optimal solution. It's just based on the knowledge that we have. So there's bounds on our brain power, or I don't know how to put that. just a note in everything that follows, the Harrison Solis text will just take that as the equation with no, they could have put the intercept in. It doesn't change the result at all. I think they wanted to simplify it. But now to start with the short run models. As much as we believe that in the economy, if I can just go back, that this situation presents itself, long run, steady state relationship. On the other hand, on the other side of that coin, we can also say dynamics matter for this outcome. So what is it now? How do we decide between, it almost seems like two opposite forces want to pull us in different ways of modeling. Furthermore, this approach presents some multicollinearity problems, and that's where we start using things like Elman lags or create those structures to include that, but we now have a way to deal with that more properly. So if we have that to avoid the multicollinearity, one way would be to difference and just estimate this model. And this is sometimes done. This is a structural var in differences. If we change it to a reduced form var, that will not appear, but the dynamics will be there. But differencing, as we said, we lose theoretical information. We lose, for instance, that important parameter that's often informative in terms of economic theory. So a possible solution is then to marry these two to construct what is referred to as an error correction model, starting from this ARDL model specification. So the few steps between 1 and 2 is simple mathematical manipulation, but taking us from an ARDL model to an ECM model, an error correction model. And when we arrive here, we have ticked now so many boxes, it's not even funny. Here we still have our long run parameters. Everything is in stationary form because that linear combination, we tested the residual of that. In essence, we know that that relationship, we know that ET is effectively YT, and the lag one period is a different story that we, oops, how do I do undo, undo, minus beta naught hat minus beta 1 hat xt minus 1. So we know that we can calculate, just using that information, we can calculate the error term and plug the error term in here. And this is effectively, there was also at one stage a method that was popular that was referred to as the one-step Engel-Granger method. And especially the Reserve Bank researchers, they use this, but yes, you can set it up and estimate everything together, but then you still have to go back and test for co-integration. So it's much of a muchness. It doesn't really matter if you do it as 2 steps or as 1. The ARDL method, Pesseron, Shin and Smith bound testing, and ARDL method will do it in 1 step. Basically do that, but go back and test for co-integration, as well as the multivariate co-integration will do this, but under the premise that there can also be another long run. and the long run will then go in, may or may not go into, say we find two co-integrating vectors, it will, the long run, there can be two long runs going into both, or not. So what other box do we tick? Every single component here is stationary, because this we've tested to find it I1, difference at once, then it's stationary. If we find that to be I1, difference at once, that is stationary, and that is basically the linear combination of the long run represented by the error term, and that will be stationary. What parameter we've put in front here, that is referred to as the error correction mechanism. And we will see why we see that, but to note is that the sign is negative. Oh, I see, there's exactly what I wrote there. Is here, and everything is stationary. And this is just my attempt to go from year to year, see what steps are necessary. So basically, to get a difference y on the left-hand side, I subtract yt minus 1 both sides, and then in order to get the delta xt here, I have to subtract gamma naught times that, both sides, and then I can collect, I bring it over this side, so I have that term, the lagged x value, and these two give me the delta x here. And so you just carry on moving closer and closer to this. So when you here, we have yt minus 1, we have an xt minus 1, we have a delta x, a delta y. We just want to bring this into a bracket so that I have this parameter in front. And if I have it's in front of the yt minus 1, so here I just have to put it below as new denominators there as well. So, and these are just numbers. We can just say that is beta naught and that is beta 1, and then we have our ECM. So mathematically, really no complicated anything. That's probably the one time there's a simple solution to a complicated problem. And this I said, I don't know if I said it, we refer to that parameter as the speed of adjustment coefficient. And we want it to be negative in order to have this act as an error correction mechanism. So all of that is kind of things that you do know or not. Those of you that told me you know your steps, is that one of the steps that so how will we implement that, and what does that story about the error correction mechanism, what does that mean? And why do we lag this? This is also by design that we want those terms lagged. Although we talk about steady state, at some point it doesn't matter. T and T minus 1 and T minus 2, there's no real force to move out of that equilibrium position. So that relationship should be true for T minus 1 and for T plus 1, etc. That's why we lag it, so that it can act as an error correction mechanism. Why should the coefficient be negative? When we are in a position of positive disequilibrium, that negative parameter will bring us back to equilibrium. If we're in a negative position of disequilibrium, that parameter that's negative will bring us back to the equilibrium from a negative position. Help us to converge back. So that helps then, so that the error term can act as a lagged error term can act as a error correction mechanism. Typically, we want that value to be between -1 and 0. Why? If it's exactly -1 and the disequilibrium is 5, it will bring us back within one period if the coefficient is 1. If it's smaller than 1, it will take longer. Technically, it can go up to -2, and we will see what will happen then. Then we will actually correct too much, and then have to correct back, and eventually converge back. And if it's exactly 0, there will be no convergence. So I think that we can see in, this is just a graphical depiction. If we are in this positive position of disequilibrium, financial crisis happens, people want to hold more money in liquid form, or so that's a position of positive disequilibrium. How do we converge back to a position of equilibrium? So if that parameter is exactly 1, it will take 1 period. If that parameter is -1/2, what will happen is if the disequilibrium position is x, it will take, after 1 period, half of that. If it's 100 units, it's measured in the measurement of the dependent variable. 50 units will be corrected after period 1. And then 50% of that, so another 25, and then 12.5, etc., until we get back to equilibrium. But unfortunately, by that time, a different shock has happened. So it's not as straightforward as that. If that parameter comes out as positive, and this will almost never happen, but if you get it, sometimes when we model difficult things, like labor markets, and we don't have good data, then it can happen. Or you have a very small sample, but occasionally that can happen. Then you know, going further with this model, put it as an equation in a system of equations, that model won't just blow up. It will just not give. You won't see it so much in your estimation, but as soon as you start do a scenario test, and there's also warnings about that, doing scenario testing with these types of models because of the Lucas critique, but we can discuss that later on, but that's the idea. And if it's bigger than, we will eventually converge back within an overshooting fashion. So let's just see how we put everything now together. We've seen this now so many times. When we estimate the long run, we said the most important questions to ask is not how well does the model fit, but do these parameters make sense? And secondly, looking at that residual and ask, do these two variables form a long-run relationship? Once we have proven co-integration, and we, in this case, found we reject the null of no co-integration at the 5% level, we can interpret to see if it makes sense. So now we can ask, what about short-run adjustment? And that is where we then go ahead and build an error correction model. Of course, now we know this is already given. It must be differenced. That residual will represent the whole long run. We lag it so that it can act as a error correction mechanism. And this is already like the first ingredients, non-negotiable, that must be there. There are several approaches to do this. There's a general to specific or specific to general. What is the general to specific? You go ahead and you literally throw everything in. Every single variable that you believe can make a contribution, and as many lags as possible. I see this light is dying now, but I have a spare battery. So this will be the general to specific. So general would be to put all of this in, say, so that's the long run, that is there, but now dynamics that can help is also lagged values of income, lagged values of, so this will measure like habit persistence, that things that you are used to spend your money on, so it will be similar to previous periods, and you see, each time you see ... So that can be minus t minus 4, all the lags. Other things that may help in the short run, interest rates, inflation expectations, wealth, and some structural variables. But we also know if you put so many things in, sometimes you have to remove a significant variable to improve the results. I can see you guys are so tired now.
Sorry.
The most two difficult days is coming. So it's almost more clean to build it up by adding not even like all the lags, but just adding one component at a time and then see how we improve. Does it help? Does it not help? Can I drop it again? And now, since we now in the true OLS world, every variable strictly must be significant. Sometimes we will keep interest rates marginally significant just to have it in our model. So this is now considering things that the theory tells us. Interest rates matter. Does it? Do you check that rate on your credit card that you pay before you tap it? Or not even, you tap your watch or your phone. Do you check your interest rate? Does it say, no, I cannot spend? So basically what I'm saying, are we interest rate sensitive? And moreover, many economies, you have a large number of people with no access to credit. So interest rate doesn't really matter in those decisions. So we do see that's why we don't include an interest rate in the long run, because of that fact for South African consumers. Maybe if we only focus on durable consumption, then it matters a little bit more. But the aggregate, where many people are literally living month to month, like salary to no salary. and it's interesting if you go out for dinner just around payday. It's like you can't almost get in, because I don't know if it's just a mental thing that people say, we have money, let's go out. But yes. So the question is, does that matter? We have to test that. Also, inflation expectations. I think that is kind of, if you believe that inflation is going to make that big screen television more expensive than the interest that you're going to pay on your credit card if you buy now, that may affect the decision. I think now with tariff expectations and things like that, that may come into play for certain things. I don't know what exactly I don't think we import a lot, but we do export to the US. And then, of course, wealth. That can help in the short run. If you have some savings, you can indeed book that ticket to go on a holiday or whatever. So maybe we must, instead of just looking at that like in a flash, but let's look at that and then we just demonstrate that in a stepwise fashion. So what do we see here? We see differences next to consumption and income, real interest rate. So that means that difference between inflation and nominal interest rates. Is that a stationary process? Is inflation expectations a stationary process? And that one is maybe debatable. And then COVID, we will never difference a dummy. If you look at that speed of adjustment parameter, is it fast, moderate, slow? Slow to moderate, the adjustment. Why do I have a green cross here? And everything else is in red, implying we have to focus on everything that's in red here. Because now the distributions are standard, so we are interested to know that everything is now significant, except maybe the constant. We may decide or not decide to drop it, but it's always better to keep it, even if it's not helping. So now we can say, well, we explain 76% of the variation. And the fact that we don't consider this is because this is already, if you write out ln yd, difference of ln yd times that, it will be that times ln yd in period t minus that times ln yd in period t minus 1. So depending if we're going down or up, the impact will be positive or negative. So all that we want to see is that it's statistically significant, that we don't say, oh, we must have a positive there. It will certainly help in this, where we have these strict upward trends in both series, but typically we don't pay so much attention because it's already at period t and t minus 1, and the signs will be different for those two periods.
So, look.
Yes.
You are basically emphasizing that once we get to this point, we should mostly focus in the research paper on the long run, the stable relationship in terms of interpretation. And
yes. Yeah, we just want to pick up all the turning points as well as we can without adding too much noise. And this is just, of course, there's a unitary test on interest rates and inflation expectations. This could potentially, I don't know if I show it here, using a breakpoint test. This is something that you could perhaps think of differencing and see if you get a better result or no. But inflation kind of, one would think of as long as we have monetary policy, but we know what happened in the 70s with the oil shocks. So that is one that perhaps we need a difference there. But just to look at that like this, let's just do it in a little bit of a stepwise fashion. If we start with what we want to have on the left-hand side is consumption, but we're going to difference it. And what we want to have on the right-hand side is the residual. And I've already used proc make residual to get this. So if I open this as an equation, I don't want ln of cons, but difference of ln of cons. So I difference that one, and I lag this one. And this is now the first. We look at that. Is it significant? And we look at this, and it will be awful. Look at the R squared. But that's exactly what we expect. It's that middle of the road steady state. We have a lot of disequilibrium above and below. So this is now where we can say, well, I just want to put the constant here so I don't have to worry that I will forget about it. And then I start say, what about income? If I add log of disposable income, and I can have it in level, or I can lag it, I mean in current period, or I can lag it. And when I get here, I don't pay attention to that. I see it is significant. I see now suddenly my R squared went from 0.12 to 0.68. So that already helped a lot picking up the dynamics. I can say, okay, habit persistence matters, so I put log of consumption -1. And that now helps a little bit. And now I can see where am I missing things, sanctions maybe, or during COVID. But what about that impact of interest rates? So this is where I add my real interest rate. And you can try current period, but I suspect the current period was less significant. Oh, it was actually significant, but maybe later on I had to go and lag it because it becomes insignificant. So leave it for now. It helps another point there. And now you, without introducing unnecessary noise, you want to implement some of the variables that matter so that in a larger model, you actually have a handle on, if you don't have an interest rate, you cannot model how monetary policy will feed through. You see, as soon as I add inflation, the interest rates become insignificant. So that was probably why I lagged that by one period. And with this, there's no right or wrong. You can see each time we add a variable, and the only last thing that I tested here was the DUM of COVID. So that served to detract from consumption, leaving us here. So all of these variables helped to pick up those turning points. And in some of the other methods, all of this will happen automatically. You don't have to add each component one by one. But you also can. There is some room to add variables that are not in the long run, only in the short run. the thing is, where do you go with this fit now? Nobody really wants to know what will happen with the difference of the log of consumption. Your boss will say, but where do we put that in the report? What will happen to the difference of the log of consumption? So we have to convert it back. And the way we're going to convert it back is by, of course, now first we have to perform diagnostic testing on this. But we can already see this residual pretty much look like a white noise process. Whether it's normal or not, it's likely to be normal. Whether there are other problems with stability in the relationship, it's unlikely. There's really, we explain quite a bit of what's going on here. How we put it in a model is, maybe I can just show it quickly and later we can discuss it a little bit more if needed. So it's simply now, the ECM contains these two components, right? The steady state, and the ECM contains the long run and some dynamic adjustment. How do we put that in one model? Because ultimately we want to show the fit of consumption. So what we do is we create a model object. And yeah, I've done it already, but maybe I can just, you know, if how I would do that, let me just do it down here and then I can, and maybe I must try and make it a little bit bigger. Will this be a table or a... models. Let me make that 18. Did it work? So basically what I want to do is I want to have, and a comment is just a single quote. I want my long run relationship and I will get it from here. But I don't have to type it because if you go to view representations, it's already here. So you can just bring it here and then my ECM, I can fetch it here from my view representations. In R, you will have to code this. So have that, but that's not good. That will not solve. What I and for furthermore, what I want here, I want consumption. So the first thing is that this is not right because what feeds from the long run is the residual. So I have to use this. So the residual is equal to the actual consumption minus bracket, close bracket. Now I can use that information to calculate consumption. Consumption will feed into this. And what is a problem is here, because that is a function. I cannot have a function as a placeholder. So I have to write that actually as lincons minus lincons minus 1. Oops. And these brackets will not break anything, but this is now still an operation. I cannot have this whole thing to the left of the equal sign, but I can simply subtract that both sides, effectively, what I do is I plus it on the other side. And now I have a system that I can solve. Consumption goes into that variable, and then I have the log of consumption, and then consumption will be e to the power of log of consumption. And this is now a set of equations that I can solve with a solver like Broyden or Gauss-Seidel. And simply how that works, we will start at the initial period. That can be it will probably be 1962 or so. And then I will work through all the periods. And each time we it's in a loop. We iteratively solve it until we find convergence. And the convergence criteria is one iteration to the second iteration. These outcomes shouldn't change with more than 5% or 1% or 0.5%. And this is how you can set up now, bring in consumption, investment, and all that, and solve as a whole, and then you can forecast with that. So shall we try that? So this is what we have up here. So what happens if we solve? I've made changes now, so it will compile again. And just a few things. What we want to do is to solve deterministically and dynamically, because a static one will just grab the actual instead of the simulated lagged value. We can decide on this will be my baseline forecast. I can add different scenarios to ask what if interest rates didn't do this but that. And so most often we don't have to worry about the solution sample. We can just go ahead. And since it's baseline, it will create every variable on the left-hand side here will also get an _0 fitted value. So if all goes well, we won't see errors. And then we can go to our objects, and if we then compare consumption and fitted consumption, we can see, you can see we lose two observations in the beginning, and what we see is that this is how well we do. The static solution will always be better than the dynamic solution. And I know consumption is one that works well. The investment one that I did, the initial periods for investment doesn't look so well. So I come here and I show you something that looks nice. And then you go back and it's like, that was all a lie. So is this the end of the road? It's just the beginning. Because now you can forecast, you can simulate different scenarios and do things like that. You can add more equations. You can model investment, you can model exports, you can model imports, you can add it together, and then you can ask what if questions. But the Lucas critique. That's why it was very popular, this type of modeling. It went from that pure demand side type of setting up behavioral equations to, yes, but what about the supply side? Most economies are constrained by supply side issues, skills and capital and all of that. So the whole new classical literature, supply side economics, and now we model wages, the labor market, the capital market. We model the monetary sector, the external sector. And we put all together, and then we forecast. So for forecasting, these are all still 100%. The Lucas critique do not affect that. But if you want to do policy analysis, what does the Lucas critique tell us? If you implement a policy change, the parameters of the model will change, potentially. Each time you want to test a monetary policy, but under the assumptions, the parameters that don't allow for that change. So that's the whole idea, that policy changes will also affect behavior. So that was when the whole movement towards rather focus on the micro foundations and do it from a DSGE model perspective. But for a long time, this is what, and now we put all the equations together, we simulate, we calibrate, which is just a fancy way of saying where we miss the target towards the end. We allow for a little bit of an, we will use, say, up to here as an exposed historic period, calibrate, and then forecast the ex ante future period. And use add factors to calibrate. And it's still in use. When I spend time with the people at the Reserve Bank that works on the QPM, they still on the side do a little bit of this as well, using the add factors, calibrating small models, and just to get a feel. So that too, alongside using VARs and structural VARs and using DSGE. So that's but between this and DSGE is a stack of micro theory, macro theory, state-space modeling, Bayesian econometrics, and regime switching, and then all of that comes together and you have this brilliant DSGE model situation. And in the hands of experts, it's a very nice thing to watch. Are we there yet? Like the kids in the car. Almost. Actually, I have a few slides to fill this last few minutes. How many slides? A few, but not too many. Like 12 or so. So that we've seen. So there's some unitary testing that should be carried out before we include those in the ECM, and all those asterisks mean rejection at the 5%, 5%, 1% for the trend and intercept model, and none. So we conclude that real interest rates are stationary as it should be. Otherwise, the Reserve Bank doesn't fulfill their mandate of using interest rates to manipulate inflation. And when we are here, now we almost full circle, because now all the distributions are standard, statistical inference is valid, and we should just do that last little step of performing diagnostic testing to conclude economically and statistically well-specified model. Here is what we've done previously. We've have the long run and the ECM, which we can code like this, which will give us that. And now we're here. Now what we saw on the first day, that slide. How we just do that practically, and it's very well implemented in the software, going through the motions of testing all these potential violations, which will culminate in a table like this. One test, and what you will note now is typically when we estimate a model y is a function of x, what we do when we have that yt is equal to beta naught plus beta 1 xt, the null there is that beta 1 is not equal to 0. Is that actually what, oh, sorry, that it is equal to 0. Is that what we want? Not really, because then everything is in vain. If we do a unitary test, it's maybe using the words what we want or what we don't want. It's not like the movie What Girls Want or those movies. It's not really, it depends. In the case of unitary testing, it's not that we absolutely want a stationary series. What we expect is to find non-stationarity, so a non-failure of the rejection of the null of a unit root. When we get to diagnostic testing, we put in the null kind of what we want in quotation marks. So we want the residuals to be normally distributed. We want no zero correlation. We want no heteroskedasticity. We want no misspecification. So all of that is, for all of that, there's a test. And that test can be a test regression with an associated test statistic. It can be just a calculated test statistic like the Jacques Barrat. And I know I say that word wrongly. I don't know what it will sound like. It sounds French to me, but maybe not even. And yeah, so most of them will be test regressions with so the Ramsey reset. There's a likelihood test, and there's what's the other test that we will do? The likelihood ratio. That's the one that we report. But there's another one, that F test, where we compare this restricted model with the unrestricted model. So we will see that details. But obviously now we want to fail to reject. So we don't want to see any p-values here below 5 or 10%. And then we conclude that everything is in order. In professional language, we will say our model is statistically well specified. And if the parameters make economic sense, we will also say it is economically well specified. We have a couple of stability diagnostics that we can look at, and we will look at some of the details quickly tomorrow morning. But recursive coefficients, and Ponzo and I have discussed recursive estimation now multiple times. She wants to use it in a PhD paper. What we want to see, these are recursive estimations, but it's just running in the background and it's not giving us all the information. But graphically we can see those parameters after a while, they kind of do not change a whole lot. And that means the model is stable. Sometimes they will change. If you think about a production function, and the capital inelasticities, if there's a move away from capital intensive production or towards capital intensive production, away from labor intensive, we will see those parameters trending in a certain way. But this is a good thing for consumption, and the parameters are like the first, oh, now it's done, but it's like the first variable in the ECM, second, third, fourth, 5, 6. So that we can also pinpoint one that doesn't behave so well. And that is the last slide.